So in this session we're going to be looking at the nucleophilic substitution reactions of haloalkanes. So first let's remind ourselves of the definition of a nucleophile. So a nucleophile is an electron pair donor. So electron pair donor is what we're looking at. And we can see that from each of our nucleophiles here, they all have an electron pair, a lone pair there that's available. You can also see that some of these nucleophiles that we have a negative charge. You can see there on the hydroxide and the cyanide ions. And I want you to notice that even though we write these as OH minus and CN minus ordinarily, when we're doing mechanisms, the negative charge, we actually put it where it belongs, which is on the oxygen in hydroxide and on the carbon in cyanide. These are the three nucleophiles that we're going to focus on then. So we're going to be looking at the hydroxide ion, cyanide ion, and then ammonia, not an ion, but it does have that lone pair available. And these lone pairs are going to be what is involved in attacking this carbon because of its delta positive charge. Remember, it's the haloalkane. So on here, this X, that is just going to be my halogen. And so because I've got a halogen there, which is going to have a higher electronegativity than the carbon, we've got a delta negative on that X and delta positive, therefore, on the carbon at the other end of the bond. And so that is where our initial attack of the lone pair is going to take place. And we're going to look at that next. So looking at the mechanism, this is the curly arrow mechanism for this nucleophilic substitution reaction. We have got our carbon X bond there with the delta positive carbon and the delta negative for our X. Remember, that's the halogen. So that is the bond that's going to be broken. And then we've got our nucleophile with its lone pair. It will always have a lone pair. And in this case, we've done one with a negative charge on. So it could be the hydroxide or it could be the cyanide. So we need to remember that we're going to start our curly arrow at the nucleophile. Remember, it's nucleophilic substitution. So the attack comes from the nucleophile, lone pair, to that delta positive carbon. And then that CX bond is what's going to break, because the X, that is what is our leaving group. That's the thing that's going to leave this haloalkane. So the resulting product, in this case, is going to contain those same three bonds that we had there originally. And now we've got a new bond to the nucleophile. Both electrons in that bond are from that lone pair that we had from the nucleophile. So that nucleophile has now lost that negative charge. And the X here now becomes X minus. And the lone pair that we have has come from that bond there that was broken, which we showed with that curly arrow. Then the lone pair from the nucleophile, that is what's formed the new carbon nucleophile bond here. So now it's become that bonding pair, effectively. Those two arrows are all that we need in the mechanism for a nucleophilic substitution of a haloalkane, where our nucleophile is either hydroxide or the cyanide ion. So some of the key things we need to know. The nucleophile must have a lone pair. Next, it's really important that the curly arrows start either at the lone pair or at a covalent bond. So we can see the beginning of our mechanism, we're starting at the lone pair on the nucleophile, and the second arrow comes from the covalent bond. It goes to X, which is our leaving group, the halogen, would be representing that as Cl or whatever in our actual mechanism, and the X minus that we produce, that has a lone pair which has come from that CX bond. And that is pretty much what you need to know. Here's a specific example. We've got chloroethane and sodium hydroxide. So the conditions you need are reflux, that's just to increase the speed of reaction, increases the rate. Then you have the chloroethane and ethanol because it won't dissolve in water, an aqueous solution of the sodium hydroxide, and that aqueous solution of sodium hydroxide and the ethanolic solution of the chloroethane, they're miscible, so you do get them mixing together so you can have a reaction. So pause the video and have a go at drawing this mechanism. First thing you need to recognise is that, of course, sodium hydroxide is ionic, so when we have that in solution, the two ions are completely separate, so you've got the hydroxide ion and the sodium ion. So the hydroxide ion is the only thing that's actually taking part in this mechanism. The sodium ion is a spectator ion, really. So then we have our curly arrow going from the lone pair to the carbon, and then this bond here is going to break, and so we end up with our product, which still is based on our ethane. So we've still got our two carbons there with their corresponding hydrogens around them, but we've now made this OH bond, and we've also got that Cl minus with the lone pair left over there. So we've made an alcohol, we've made ethanol from our chloroethane, and then we have the chloride ion here in our mechanism. We just need to show the chloride ion. We can, of course, draw or write an overall equation for this. So we could have this here. We said we had sodium hydroxide, so we can put that in there. Then our structural formula of the ethanol, and then we would then have sodium chloride in our solution. And that's the same pattern that we would see anytime we take a haloalkane like this, react it with sodium hydroxide or potassium hydroxide. We're going to make the alcohol and the chloride salt there. Let's look at another example. So this time we've got chloroethane and potassium cyanide. Conditions are the same, reflux. Chloroethane is in ethanol to dissolve it, and then we have the aqueous solution of the potassium cyanide. So remember, that means that we've got potassium ions and completely separate cyanide ions, no covalent bonds between them. So I want you to have a go at drawing the mechanism. Here we go. So we've got the cyanide ion here. Remember, the minus has to be above the carbon. That negative charge is on the carbon where the lone pair is. Line here, curly arrow, from the carbon to the delta positive carbon in our haloalkane, then breaking this bond because my chlorine is my leaving group, and then I'm going to make that product. So what I have here is my ethane backbone of my molecule here, same number of hydrogens and carbons as I had previously. Only thing that is different is that now I have made this bond here, that CN is now attached. And what is left over, it's my leaving group, of course, negative chlorine and a lone pair on there. So just as we did before, we could write a general structural formula equation here. And if you're ever asked to write an equation for something that is an organic reaction, don't do molecular formula because there's too many options that could be. It's too ambiguous because you can have various isomers. So always do your structural formula at a minimum, and therefore we end up here CH2CN plus KCl. Okay, and that's what we would have here. Now for naming, we started off here with our haloalkane with chloroethane. We've added it to the potassium cyanide. So as the ion here with the potassium is called cyanide, but when we have this bonded on here, so when we've got this CN group here, this is now 3 carbons, so it's propane nitrile. So 2 things to notice here. First of all, we've extended the carbon chain, so we've got 1, 2, 3 carbons, so it's a really useful reaction for making longer carbon chains. So therefore we now have propane here, and also it's not just propan, you need this E in the middle. Okay, so it's propane nitrile, and nitrile is representing that functional group there at the end of the C triple bond to N. And just so we're clear about that, this is what we have at the end. It's that, and then 3 bonds there to the nitrogen, which makes sense because we're familiar with seeing nitrogen with 3 bonds around it and carbon with 4 bonds around it. So just so we know that that's what's happening there. Next, let's take a look at the nucleophilic substitution reaction of a haloalkane with ammonia. So conditions: sealed container under pressure. We've got the halogenoalkane in ethanol and a concentrated solution of ammonia. And for the mechanism, we can just look at that regular general representation of our haloalkane. And here we have the ammonia with no charge, but the lone pair, so we must have the lone pair there on the nitrogen. It's going to go in and attack that carbon, which would be our delta positive carbon, delta negative there on our halogen, and then curly arrow from the bond to there. And what do we make? Well, it's a little more complicated this time. Because we have got already 3 bonds on our ammonia, we now end up with a nitrogen atom with 4 bonds around it. This means it has a positive charge. So this isn't our finished product. We still have a further step to go. And what we have is we have another ammonia molecule which can come along here with its lone pair, and this can then attack here. So we have that curly arrow going from the lone pair to this hydrogen, and so that ammonia is picking up that hydrogen. We need to break another bond, and this time the bond that we break, we're going to break from here, and the arrow is going into that positive nitrogen. And so for the final product, we now have this product here, this amine. So we've got an NH2 in here on the end of the chain, and this ammonia here, when it picked up this hydrogen, became NH4+. And if we think about what we started with here with the X, that would still be present. So at the ends here, we've got NH4+ and X minus, or you may write that just as NH4X. So for example, if we'd started off with a bromoalkane, this would be NH4Br, ammonium bromide. So what we have here is another example, bromoethane and excess ammonia. So what I would like you to do is outline the mechanism, so that means draw the mechanism with the curly arrows for this particular reaction, and also write an equation showing the structural formula for the reaction overall. So pause the video now and have a go at that. So here's what we should have. The nucleophile with the lone pair, you must have the lone pair. Very clear curly arrow coming from the lone pair to this carbon, which is bonded to the bromine. Then we have the arrow from the bond here direct to the Br. Then on this side we have another ammonia. This ammonia is going to pick up that hydrogen. This bond must be from the hydrogen that's been picked up by the ammonia. You could have drawn it to that one, but then it would have to be this bond. So in this case it's this bond here. It's going in, that curly arrow, it's going in towards that positive nitrogen. So therefore we end up with a nitrogen with 3 bonds around it, so that's our amine there. And then we've got NH4Br, that's our ammonium bromide. And here we see our overall equation using the structural formula. So we have bromoethane, ammonia, check you've got this correct, it's 2 equivalents of ammonia, giving us ethylamine and ammonium bromide. So it's also worth noting that the ammonia is acting in 2 different ways in this reaction here. So first of all here, this is ammonia as a nucleophile attacking this delta positive carbon to make a new bond. And secondly here in this second step, this is ammonia acting as a base, where it's going to be a proton acceptor and it's picking up this hydrogen there to form this ammonium. And one last thing to consider before we finish is that we have excess ammonia here, and the reason that we require that. So the reason we have this excess of ammonia is to encourage the yield to be high of this, our primary amine, because this amine that we produce actually has a lone pair here, and so therefore it can also act as a nucleophile. So if we don't have that excess of ammonia, so that the majority of our bromoethane has already reacted, so here, then this product could go on to react as a nucleophile with the bromoethane, and that will lead to other products. That would lead to a secondary amine and a tertiary amine, and sometimes we also get a quaternary ammonium salt. This is something that we'll see in the amines chapter next year, but for now I just want you to be aware that that's the reason that we need to use this excess of ammonia to ensure a high yield of the primary amine.